Overview. A data structure is the organization of data in a computer's memory or in a disk file. The correct choice of data structure allows major improvements in program efficiency. Examples of data structures are arrays, stacks, and linked lists. An algorithm is a procedure for carrying out a particular task. In Java, an algorithm is usually implemented by a class method. Many of the data structures and algorithms described in this book are most often used to build databases. Some data structures are used as programmers' tools. They help execute an algorithm. Other data structures model real-world situations, such as telephone lines running between cities. A database is a unit of data storage composed of many similar records. A record often represents a real-world object, such as an employee or a car part. A record is divided into fields. Each field stores one characteristic of the object described by the record. A key is a field in a record that's used to carry out some operation on the data. For example, personnel records might be sorted by a last name field. A database can be searched for all records whose key field has a certain value. This value is called a search key. Arrays. Arrays in Java are objects created with a new operator. Unordered arrays offered fast insertion but slow searching and deletion. Wrapping an array in a class protects the array from being inadvertently altered. A class interface is composed of the methods and occasionally fields that the class user can access. A class interface can be designed to make things simple for the class user. A binary search can be applied to an ordered array. The logarithm to the base b of a number a is roughly the number of times you can divide a by b before the result is less than 1. Linear searches require time proportional to the number of items in an array. Binary searches require time proportional to the logarithm of the number of items. Big O notation provides a convenient way to compare the speed of algorithms. An algorithm that runs in O1 time is the best, O log n is good, ON is fair, and ON2 is pretty bad. Simple sorting. The sorting algorithms in this chapter all assume an array as a data storage structure. Sorting involves comparing the keys of data items in the array and moving the items references to the items around until they're in sorted order. All the algorithms in this chapter execute in ON2 time. Nevertheless, some can be substantially faster than others. An invariant is a condition that remains unchanged while an algorithm runs. The bubble sort is the least efficient, but the simplest sort. The insertion sort is the most commonly used of the ON2 sorts described in this chapter. A sort is stable if the order of elements with the same key is retained. None of the sorts in this chapter require more than a single temporary variable, in addition to the original array. Stacks and queues. Stacks, queues, and priority queues are data structures usually used to simplify certain programming operations. In these data structures, only one data item can be accessed. A stack allows access to the last item inserted. The important stack operations are pushing inserting an item onto the top of the stack and popping removing the item that's on the top. A queue allows access to the first item that was inserted. The important queue operations are inserting an item at the rear of the queue and removing the item from the front of the queue. A queue can be implemented as a circular queue, which is based on an array in which the indices wrap around from the end of the array to the beginning. A priority queue allows access to the smallest or sometimes the largest item. The important priority queue operations are inserting an item in sorted order and removing the item with the smallest key. These data structures can be implemented with arrays or with other mechanisms such as linked lists. Ordinary arithmetic expressions are written in infix notation, so called because the operator is written between the two operands. In postfix notation, the operator follows the two operands. Arithmetic expressions are typically evaluated by translating them to postfix notation and then evaluating the postfix expression. A stack is a useful tool both for translating an infix to a postfix expression and for evaluating a postfix expression. Linked lists. A linked list consists of one linked list object and a number of link objects. The linked list object contains a reference, often called first, to the first link in the list. Each link object contains data and a reference, often called next, to the next link in the list. A next value of null signals the end of the list. Inserting an item at the beginning of a linked list involves changing the new link's next field to point to the old first link and changing first to point to the new item. Deleting an item at the beginning of a list involves setting a first to point to first. Next. To traverse a linked list, you start at first and then go from link to link, using each link's next field to find the next link. A link with a specified key value can be found by traversing the list. Once found, an item can be displayed, deleted, or operated on in other ways. A new link can be inserted before or after a link with a specified key value, following a traversal to find this link. A double-ended list maintains a pointer to the last link in the list, often called last, as well as to the first. A double-ended list allows insertion at the end of the list. An abstract data type ADT is a data storage class considered without reference to its implementation. Stacks and queues are ADTs. They can be implemented using either arrays or linked lists. In a sorted linked list, the links are arranged in order of ascending or sometimes descending key value. Insertion in a sorted list takes O(n) time because the correct insertion point must be found. Deletion of the smallest link takes O(1) time. In a doubly linked list, each link contains a reference to the previous link as well as the next link. A doubly linked list permits backward traversal and deletion from the end of the list. An iterator is a reference, encapsulated in a class object, that points to a link in an associated list. Iterator methods allow the user to move the iterator along the list and access the link currently pointed to. An iterator can be used to traverse through a list, performing some operation on selected links or all links. Recursion. A recursive method calls itself repeatedly, with different argument values each time. Some value of its arguments causes a recursive method to return without calling itself. This is called the base case. When the innermost instance of a recursive method returns, the process unwinds by completing pending instances of the method, going from the latest back to the original call. A triangular number is the sum of itself and all numbers smaller than itself. Number means integer in this context. For example, the triangular number of 4 is 10, because 4 plus 3 plus 2 plus 1 equal 10. The factorial of a number is the product of itself and all numbers smaller than itself. For example, the factorial of 4 is 4, 3, 2, 1 equal 24. Both triangular numbers and factorials can be calculated using either a recursive method or a simple loop. The anagram of a word, all possible combinations of its n letters can be found recursively by repeatedly rotating all its letters and anagramming the rightmost n1 of them. A binary search can be carried out recursively by checking which half of a sorted range the search key is in, and then doing the same thing with that half. The Towers of Hanoi puzzle consists of 3 towers and an arbitrary number of rings. The Towers of Hanoi puzzle can be solved recursively by moving all but the bottom disk of a subtree to an intermediate tower, moving the bottom disk to the destination tower, and finally moving the subtree to the destination. Merging 2 sorted arrays means to create a third array that contains all the elements from both arrays in sorted order. In Recursion, 1-element subarrays of a larger array are merged into 2-element subarrays. 2-element subarrays are merged into 4-element subarrays, and so on until the entire array is sorted. Recursion requires O(n) log n time. Recursion requires a workspace equal in size to the original array. For triangular numbers, factorials, anagrams, and the binary search, the recursive method contains only one call to itself. There are 2 shown in the code for the binary search, but only one is used on any given pass through the method's code. For the Towers of Hanoi and Recursion, the recursive method contains 2 calls to itself. Any operation that can be carried out with recursion can be carried out with a stack. A recursive approach may be inefficient. If so, it can sometimes be replaced with a simple loop or a stack-based approach. Advanced sorting. The shell sort applies the insertion sort to widely spaced elements, then less widely spaced elements, and so on. The expression n sorting means sorting every nth element. A sequence of numbers, called the interval sequence, or gap sequence, is used to determine the sorting intervals in the shell sort. A widely used interval sequence is generated by the recursive expression hour equal 3 hours plus 1, where the initial value of h is 1. If an array holds 1000 items, it could be 364 sorted, 121 sorted, 40 sorted, 13 sorted, 4 sorted, and finally 1 sorted. The shell sort is hard to analyze, but runs in approximately on log n2 time. This is much faster than the on2 algorithms like insertion sort, but slower than the on log n algorithms like quicksort. To partition an array is to divide it into two subarrays, one of which holds items with key values less than a specified value, while the other holds items with keys greater than or equal to this value. The pivot value is the value that determines into which group an item will go during partitioning. Items smaller than the pivot value go in the left group. Larger items go in the right group. In the partitioning algorithm, two array indices, each in its own while loop, start at opposite ends of the array and step toward each other, looking for items that need to be swapped. When an index finds an item that needs to be swapped, its while loop exits. When both while loops exit, the items are swapped. When both while loops exit, and the indices have met or passed each other, the partition is complete. Partitioning operates in linear on time, making n plus 1 or 2 comparisons and fewer than n, 2 swaps. The partitioning algorithm may require extra tests in its inner while loops to prevent the indices running off the ends of the array. Quicksort partitions an array and then calls itself twice recursively to sort the two resulting subarrays. Subarrays of one element are already sorted. This can be a base case for quicksort. The pivot value for a partition in quicksort is the key value of a specific item, called the pivot. In a simple version of quicksort, the pivot can always be the item at the right end of the subarray. During the partition, the pivot is placed out of the way on the right, and is not involved in the partitioning process. Later the pivot is swapped again, into the space between the two partitions. This is its final sorted position. In the simple version of quicksort, performance is only on2 for already sorted or inversely sorted data. In a more advanced version of quicksort, the pivot can be the median of the first, last, and center items in the subarray. This is called median of 3 partitioning. Median of 3 partitioning effectively eliminates the problem of on2 performance for already sorted data. In median of 3 partitioning, the left, center, and right items are sorted at the same time the median is determined. The sort eliminates the need for the end-of-array tests in the inner while loops in the partitioning algorithm. Quicksort operates in on log 2n time except when the simpler version is applied to already sorted data. Subarrays smaller than a certain size, the cutoff, can be sorted by a method other than quicksort. The insertion sort is commonly used to sort subarrays smaller than the cutoff. The insertion sort can also be applied to the entire array, after it has been sorted down to a cutoff point by quicksort. The radix sort is about as fast as quicksort but uses twice as much memory. Binary trees. Trees consist of nodes, circles connected by edges, lines. The root is the topmost node in a tree. It has no parent. In a binary tree, a node has at most 2 children. In a binary search tree, all the nodes that are left descendants of node A have key values less than A. All the nodes that are A's right descendants have key values greater than or equal to A. Trees perform searches, insertions, and deletions in O log n time. Nodes represent the data objects being stored in the tree. Edges are most commonly represented in a program by references to a node's children and sometimes to its parent. Traversing a tree means visiting all its nodes in some order. The simplest traversals are pre-order, in-order, and post-order. An unbalanced tree is one whose root has many more left descendants than right descendants, or vice versa. Searching for a node involves comparing the value to be found with the key value of a node, and going to that node's left child if the key search value is less, or to the node's right child if the search value is greater. Insertion involves finding the place to insert the new node and then changing a child field in its new parent to refer to it. An in-order traversal visits nodes in order of ascending keys. Pre-order and post-order traversals are useful for parsing algebraic expressions. When a node has no children, It can be deleted by setting the child field and its parent to null. When a node has one child, it can be deleted by setting the child field and its parent to point to its child. When a node has two children, it can be deleted by replacing it with its successor. The successor to a node A can be found by finding the minimum node in a subtree whose root is A's right child. In the deletion of a node with two children, different situations arise, depending on whether the successor is the right child of the node to be deleted or one of the right child's left descendants. Nodes with duplicate key values may cause trouble in arrays because only the first one can be found in a search. Trees can be represented in the computer's memory as an array, although the reference-based approach is more common. A Huffman tree is a binary tree but not a search tree used in a data compression algorithm called Huffman coding. In the Huffman code, the characters that appear most frequently are coded with the fewest bits, and those that appear rarely are coded with the most bits. Red-black trees. It's important to keep a binary search tree balanced to ensure that the time necessary to find a given node is kept as short as possible. Inserting data that has already been sorted can create a maximally unbalanced tree, which will have search times of O(n). In the red-black balancing scheme, each node is given a new characteristic, a color that can be either red or black. A set of rules, called red-black rules, specifies permissible ways that nodes of different colors can be arranged. These rules are applied while inserting or deleting a node. A color flip changes a black node with two red children to a red node with two black children. In a rotation, one node is designated the top node. A right rotation moves the top node into the position of its right child, and the top node's left child into its position. A left rotation moves the top node into the position of its left child, and the top node's right child into its position. Color flips, and sometimes rotations, are applied while searching down the tree to find where a new node should be inserted. These flips simplify returning the tree to red-black correctness following an insertion. After a new node is inserted, red-red conflicts are checked again. If a violation is found, appropriate rotations are carried out to make the tree red-black correct. These adjustments result in the tree being balanced, or at least almost balanced. Adding red-black balancing to a binary tree has only a small negative effect on average performance, and avoids worst-case performance when the data is already sorted. 2-3-4 trees in external storage. A multi-way tree has more keys and children than the binary tree. A 2-3-4 tree is a multi-way tree with up to 3 keys and 4 children per node. In a multi-way tree, the keys in a node are arranged in ascending order. In a 2-3-4 tree, all insertions are made in leaf nodes, and all leaf nodes are on the same level. 3 kinds of nodes are possible in a 2-3-4 tree. A 2 node has 1 key and 2 children, a 3 node has 2 keys and 3 children, and a 4 node has 3 keys and 4 children. There is number 1 node in a 2-3-4 tree. In a search in a 2-3-4 tree, at each node the keys are examined. If the search key is not found, the next node will be child 0 if the search key is less than key 0, child 1 if the search key is between key 0 and key 1, child 2 if the search key is between key 1 and key 2, and child 3 if the search key is greater than key 2. Insertion into a 2-3-4 tree requires that any full node be split on the way down the tree, during the search for the insertion point. Splitting the root creates 2 new nodes. Splitting any other node creates 1 new node. The height of a 2-3-4 tree can increase only when the root is split. There is a 1-to-1 correspondence between a 2-3-4 tree and a red-black tree. To transform a 2-3-4 tree into a red-black tree, make each 2 node into a black node, make each 3 node into a black parent with a red child, and make each 4 node into a black parent with 2 red children. When a 3 node is transformed into a parent and child, either node can become the parent. Splitting a node in a 2-3-4 tree is the same as performing a color flip in a red-black tree. A rotation in a red-black tree corresponds to changing between the 2 possible orientations slants when transforming a 3 node. The height of a 2-3-4 tree is less than log 2n. Search times are proportional to the height. The 2-3-4 tree wastes space because many nodes are not even half full. A 2-3 tree is similar to a 2-3-4 tree, except that it can have only 1 or 2 data items and 1, 2, or 3 children. Insertion in a 2-3 tree involves finding the appropriate leaf and then performing splits from the leaf upward, until a non-full node is found. External storage means storing data outside of main memory, usually on a disk. External storage is larger, cheaper per byte, and slower than main memory. Data in external storage is typically transferred to and from main memory a block at a time. Data can be arranged in external storage in sequential key order. This gives fast search times but slow insertion and deletion times. A B tree is a multi-way tree in which each node may have dozens or hundreds of keys and children. There is always one more child than there are keys in a B tree node. For the best performance, a B tree is typically organized so that a node holds one block of data. If the search criteria involve many keys, a sequential search of all the records in a file may be the most practical approach. Hash tables. A hash table is based on an array. The range of key values is usually greater than the size of the array. A key value is hashed to an array index by a hash function. An English language dictionary is a typical example of a database that can be efficiently handled with a hash table. The hashing of a key to an already filled array cell is called a collision. Collisions can be handled in 2 major ways: open addressing and separate chaining. In open addressing, data items that hash to a full array cell are placed in another cell in the array. In separate chaining, each array element consists of a linked list. All data items hashing to a given array index are inserted in that list. We discuss 3 kinds of open addressing: linear probing, quadratic probing, and double hashing. In linear probing, the step size is always 1, so if x is the array index calculated by the hash function, the probe goes to x, x plus 1, x plus 2, x plus 3, and so on. The number of such steps required to find a specified item is called the probe length. In linear probing, contiguous sequences of filled cells appear. They are called primary clusters, and they reduce performance. In quadratic probing, the offset from x is the square of the step number, so the probe goes to x, x plus 1, x plus 4, x plus 9, x plus 16, and so on. Quadratic probing eliminates primary clustering but suffers from the less severe secondary clustering. Secondary clustering occurs because all the keys that hash to the same value follow the same sequence of steps during a probe. All keys that hash to the same value follow the same probe sequence because the step size does not depend on the key, but only on a hash value. In double hashing, the step size depends on the key and is obtained from a secondary hash function. If the secondary hash function returns a value s in double hashing, the probe goes to x, x plus s, x plus 2s, x plus 3s, x plus 4s, and so on, where s depends on the key but remains constant during the probe. The load factor is the ratio of data items in a hash table to the array size. The maximum load factor in open addressing should be around 0.5. For double hashing at this load factor, searchers will have an average probe length of 2. Search times go to infinity as load factors approach 1.0 inches open addressing. It's crucial that an open addressing hash table does not become too full. A load factor of 1.0 is appropriate for separate chaining. At this load factor, a successful search has an average probe length of 1.5, and an unsuccessful search, 2.0. Probe lengths in separate chaining increase linearly with load factor. A string can be hashed by multiplying each character by a different power of a constant, adding the products, and using the modulo operator to reduce the result to the size of the hash table. To avoid overflow, we can apply the modulo operator at each step in the process, if the polynomial is expressed using Horner's method. Hash table sizes should generally be prime numbers. This is especially important in quadratic probing and separate chaining. Hash tables can be used for external storage. One way to do this is to have the elements in the hash table contain disk file block numbers, heaps. In an ascending priority queue, the item with the largest key is said to have the highest priority. It's the smallest item in a descending queue. A priority queue is an abstract data type ADT that offers methods for insertion of data and removal of the largest or smallest item. A heap is an efficient implementation of an ADT priority queue. A heap offers removal of the largest item and insertion in log n time. The largest item is always in the root. Heaps do not support ordered traversal of the data, locating an item with a specific key, or deletion. A heap is usually implemented as an array representing a complete binary tree. The root is at index 0 and the last item at index n1. Each node has a key less than its parents and greater than its children. An item to be inserted is always placed in the first vacant cell of the array and then trickled up to its appropriate position. When an item is removed from the root, it's replaced by the last item in the array, which is then trickled down to its appropriate position. The trickle-up and trickle-down processes can be thought of as a sequence of swaps, but are more efficiently implemented as a sequence of copies. The priority of an arbitrary item can be changed. First, its key is changed. Then, if the key was increased, the item is trickled up, but if the key was decreased, the item is trickled down. A heap can be based on a binary tree, not a search tree that mirrors the heap structure. This is called the tree heap. Algorithms exist to find the last occupied node or the first free node in a tree heap. Heapsort is an efficient sorting procedure that requires log n time. Conceptually, Heapsort consists of making n insertions into a heap, followed by n removals. Heapsort can be made to run faster by applying the trickle-down algorithm directly to n2 items in the unsorted array, rather than inserting n items. The same array can be used for the initial unordered data, for the heap array, and for the final sorted data. Thus, Heapsort requires no extra memory. Graphs. Graphs consist of vertices connected by edges. Graphs can represent many real-world entities, including airline routes, electrical circuits, and job scheduling. Search algorithms allow you to visit each vertex in a graph in a systematic way. Searches are the basis of several other activities. The two main search algorithms are depth-first search DFS and breadth-first search BFS. The depth-first search algorithm can be based on a stack. The breadth-first search algorithm can be based on a queue. A minimum spanning tree MST consists of the minimum number of edges necessary to connect all graph's vertices. A slight modification of the depth-first search algorithm on an unweighted graph yields its minimum spanning tree. In a directed graph, edges have a direction often indicated by an arrow. A topological sorting algorithm creates a list of vertices arranged so that a vertex A precedes a vertex B in the list if there's a path from A to B. A topological sort can be carried out only on a DAG, a directed acyclic no-cycles graph. Topological sorting is typically used for scheduling complex projects that consist of tasks contingent on other tasks. Warshall's algorithm finds whether there is a connection of either one or multiple edges from any vertex to any other vertex. Weighted graphs. In a weighted graph, edges have an associated number called the weight, which might represent distances, costs, times, or other quantities. The minimum spanning tree in a weighted graph minimizes the weights of the edges necessary to connect all the vertices. An algorithm using a priority queue can be used to find the minimum spanning tree of a weighted graph. The minimum spanning tree of a weighted graph models real-world situations such as installing utility cables between cities. The shortest path problem in a non-weighted graph involves finding the minimum number of edges between two vertices. Solving the shortest path problem for weighted graphs yields the path with the minimum total edge weight. The shortest path problem for weighted graphs can be solved with Dijkstra's algorithm. The algorithms for large, sparse graphs generally run much faster if the adjacency list representation of the graph is used rather than the adjacency matrix. The all-pairs shortest path problem is to find the total weight of the edges between every pair of vertices in a graph. Floyd's algorithm can be used to solve this problem. Some graph algorithms take exponential time and are therefore not practical for graphs with more than a few vertices.